All right, let's talk about Java's Object-Oriented Programming, or OOP. Now that might sound a little academic, but these are the absolute cornerstones for building the complex, powerful software we all use every single day. We're going to break down exactly what they are and why they matter so much.
So picture this. You're trying to build a huge piece of software. You've got different kinds of users, tons of different features. It's a mess of complexity. The absolute last thing you want to be doing is writing the same chunks of code over and over again. So the big question is, how do you build something that big and complex without getting bogged down in repetition? Well, that's the exact problem we're going to solve today.
And here's how we're going to do it. First, we'll dive into the power of reusability. Then, we'll get into how to build these complex family trees of code. After that, we'll lay down some ground rules to keep everything organized, learn how to design the perfect blueprint, and finally, figure out how to handle things when they, inevitably go wrong. Okay, our first big pillar is all about one simple idea. Don't reinvent the wheel. In programming, this is a concept called inheritance, and it's pretty much the foundation of code reusability.
The best way to think about it is like genetics, seriously. A child inherits traits from their parent, right? It's the same in Java. You can create a new child class that automatically gets all the methods and variables from an existing parent class. This is awesome because it means you only have to write those common features one time in the parent, and all the children just get them for free.
The logic behind this whole thing is something called the ISA relationship. It's a super simple but really powerful test. Just ask yourself, does it make sense to say a programmer is an employee? Yep, of course it does. And that means the programmer class can inherit from the employee class. It'll automatically get stuff like a salary or an employee ID, but it can still add its own unique things like programming languages. So why is this such a big deal? Well, the benefits are just massive. You're reusing code, which saves a ridiculous amount of time and effort. You can easily add new features to existing classes, and you unlock this really powerful idea called runtime polymorphism. That's a fancy term, but it basically gives your code the flexibility to treat different types of objects in the same way, which makes it way easier to manage and adapt as it runs.
But inheritance isn't just a simple one-to-one thing. You can actually structure these parent-child relationships in a few different ways, kind of like building out a whole family tree for your code. Let's check out the most common patterns.
First up, you've got the most straightforward version, single inheritance. It's just one parent, one child. That programmer inheriting from employee, perfect example. It's clean, it's direct, super easy to follow. Then things can get a little more interesting. You can chain these relationships together in what's called multi-level inheritance. So a child class inherits from a parent, which in turn inherits from a grandparent. You could imagine a senior developer inheriting from a developer, which inherits from an employee. Each step down the chain gets more specific, but keeps all the traits from the ones about it. And finally, there's hierarchical inheritance. This is where you have one single parent class that acts as a foundation for a bunch of different child classes. For example, you could have manager, developer, and designer all inheriting from that same employee class. They all share the core employee stuff, but then they each go off and develop their own unique skills. Okay, let's pause for a second because this is a spot where a lot of people get tripped up. Overloading versus overriding. They sound similar, but they're totally different. Overloading is when you have methods with the exact same name, but inside the same class, and they just take different inputs. Overriding, on the other hand, is all about inheritance. That's when a child class decides to create its own special version of a method it got from its parent using the exact same name and the exact same parameters. So, now that we're building these code family trees, we need some rules of the road to manage how they all interact with each other. And for that, Java gives us two really important keywords, super and final. Think of the super keyword as a direct hotline to the parent class. Let's say both the parent and the child have a method with the same name, like display details. If you're in the child class and you call that method, you'll get the child's version. But what if you specifically need the parent's version? That's when you use super. It lets you reach up and say, hey, I don't want my version, I want the one from my immediate parent.
And then there's the final keyword, which is all about making things permanent and locking them down. If you make a variable final, its value can never ever be changed. It's basically a constant. If you make a method final, no child class is allowed to overwrite it. And if you make an entire class final, that's it. It's the end of the line. No other class can inherit from it, period.
All right, so we've got ways to reuse code and ways to set rules. But how do we make sure our software has a consistent, logical design from the very beginning?
Well, that's where our next pillar, abstraction, comes into play. This is all about creating a blueprint that other classes are forced to follow.
Abstraction. It sounds like a really complex idea, but I promise you use it every single day. Think about driving a car. You use a steering wheel, a gas pedal, and a brake. You don't need to know how the engine's combustion cycle works or what the transmission is doing. All that complexity is hidden. You're only shown the essential controls you need. Abstraction in code does the exact same thing. It hides all the messy inner workings and just shows a simple, clean interface to the outside world.
Now, to create these blueprints in Java, we have two main tools, abstract classes and interfaces. Here's the simple way to think about it. An abstract class can be a partial blueprint. It can provide some methods that are already built, but leave others for the child classes to figure out. An interface, on the other hand, is a 100% pure blueprint. It just defines the rules, what methods must exist, with zero implementation. But here's the real game changer. A class can only inherit from one abstract class, but it can implement many interfaces at once. This is how Java gets a lot of the power of multiple inheritance, but in a much safer, more organized way.
Okay, we've built our software. It's got reusable parts, it follows a solid blueprint, but what happens when it runs into the messy, unpredictable real world? You know, when a user types in their name instead of their age, or the code tries to divide a number by 0. We need a system to handle the unexpected without the whole program just crashing and burning. Here's the classic example. You just can't divide by 0. Mathematically, it's undefined. So if your program gets to a line of code like this and tries to run it, it's going to hit a major roadblock. So what happens then? Well, you get this. A big, scary-looking error message called an exception. And if you don't have a plan in place to deal with this error will stop everything in its tracks, and your entire program will crash. That's not ideal. We need a safety net. And here is our safety net, the try-catch finally block. The easiest way to remember this is to think of a trapeze act. The try block is where you put the dangerous code. That's the trapeze artist attempting their high-flying trick. The catch block is the safety net waiting below. If the artist falls, if an exception happens, this block catches it and handles the problem gracefully so the show can go on. And the finally block, that's the part that always happens, whether the trick succeeded or not. It's like the artist taking a bow at the end. It's perfect for crucial cleanup code that has to run no matter what. And that's pretty much it. Reusability through inheritance, a solid structure with abstraction, and resilience thanks to exception handling. These aren't just technical terms. They're the core ideas that keep software from becoming a chaotic, fragile mess. They're what allow developers to build those amazing, sophisticated apps that we all rely on. Which kind of leaves you with one last thought. The next time you open up your favorite app, just think for a second, which of these pillars is doing the heavy lifting behind the scenes to make your experience so seamless?